Hi everybody, so I'm going to walk through the FRQs from your semester exam review. We'll start with problem number 1. So on problem number 1, they've given you this chart, which is velocity in miles per minute versus minutes, and they ask you a series of questions. So part A asks you to use a midpoint Riemann sum with 4 subintervals of equal length. So you notice the whole interval is 0 to 40. So 4 intervals of equal length will be 10 wide. And they're all equal subintervals, right? So the width of each interval is going to be 10. Now, midpoint means you want the height at the midpoints of each of these. So the interval from 0 to 10, the midpoint is 5. The height there is 9.2. The interval from 10 to 20, the midpoint's 15. The height is 7. And so forth. And so on. And when you do that calculation, you get 229. Now, since the area, this is area under a curve that's miles per minute versus minutes, the units for that would be miles per minute times minutes, which is in miles. And then the meaning of that is it's the distance the plane flew from 0 to 40 minutes. So you need to have the meaning, the number, and the units for both the answer and the endpoints. All right, part B. Based on the values in the table, what's the smallest number of instances in which the acceleration of the plane could equal 0? So if you look at the way the velocities are going, acceleration is slope of velocity, right? And the problem tells you right here that v is a differentiable function, meaning it's never undefined, right? So basically, if I look at this and I see any place where it goes from positive to negative or negative to positive, increasing to decreasing or decreasing to increasing, in order to switch, the slope actually has to be 0. So let's see, it's going up here again, and down from here to here. So somewhere in here it changes direction, and basically that means because it's differentiable, the slope would have to be 0. Down, 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 up. There's another change in direction. Well, it stays the same there, but and then up. So there's really only 2 places, because the velocity changes from increasing to decreasing or decreasing to increasing, and the velocity is differentiable. All right, part C. They give you this function here and ask you to use this to find the acceleration. So the first thing you know is velocity is the derivative of acceleration. So we would take the derivative of that. Derivative of 6 becomes 0 because the chain rule, the derivative of cosine of t over 10 is negative 1/10 sine of t over 10, and the derivative of the second term would be 3 cosine of 7t over 40 times 7 over 40 because of the chain rule. And then I want to plug 23 into that. And I believe when I do, I get negative 0.408. Now, part D says, using the table to approximate v prime with 12.5. So when you're approximating a derivative, that means we want to find an a-rock. And if you're approximating at 12.5, you want to pick the a-rock that's between the points closest to 12.5. So 12.5 falls between 10 and 15. So we're going to find the a-rock between 12 and 10 and 15. So let's see, change in y. Can't see that. It's 9.5, I believe. It's 2.5 over 5, which is, sorry, negative 5, and it's negative 1/2. And then we want units. So we wanted units on part C as well. And the units on that were going to be miles per minute squared. And the units here are in miles per minute. And your explanation could go a couple of different ways. You could say it's the average acceleration between 10 and 15 minutes, or you can say it's an approximation of the instantaneous acceleration at 12.5, and I forgot my prime, at 12.5 minutes. So that's question number 1. Question number 2. So part A, explain why there must be a value for r. We're looking at h of r, which is the same level as the function. So I'm going to think in terms of, and it's not a rate of change, so I'm going to think in terms of the intermediate value theorem here. I'm going to start by finding h of 1, which is f of g of 1 minus 6. G of 1 is 2, and f of 2 is 9. And then I'm going to find h of 3, following the same process. And then we notice that negative 5 is in between 3 and negative 7. And this is important, f and g are differentiable, and that means h, because it's just a composition of those things, is also differentiable. So h is differentiable, and negative 7 is less than, negative 5 is less than 3. So by the intermediate value theorem, h of r must equal negative 5 at some point. Now for part B, notice for part B they're asking about h prime, which is a rate of change, and that should introduce the idea of the possibility of using the mean value theorem. So if I look at the mean value theorem for this same interval, we already said that h is differentiable, and remember the mean value theorem involves finding the a-rock and then comparing it to an i-rock. So the a-rock in this interval would be the 2 y values that we just found, not a negative 3, it's a 3. There we go. Over the x values. That's 10 over negative 2, which is negative 5. So we were looking for h prime to be negative 5. The a-rock is that. So by the mean value theorem, the derivative must equal negative 5. Part C. Let r of x be a function such as r prime is h of x, and select every adjective that applies to the graph at x equals 2. So r prime is h. Let me fix that. R prime of 2 is h of 2. And h of 2, we haven't found yet. That's f of g of 2 minus 6. And so g of 2 is 3. And f of 3 is 10. Now 4 is greater than 0. So since the derivative is positive, that means it's increasing. By the way, this chain, r prime of 2 is greater than 0. You don't have to rewrite it there because you've shown it in the chain of work. And then for concavity, we have to look at the second derivative, which is the derivative of h. And the derivative of h, if we found the derivative of x, we'd have to use the chain rule. F prime of g of 2 times g prime of 2. And of course, the negative 6, the derivative of that is 0. So g of 2 is 3. And g prime of 2 is 1. And then f prime of 3 is negative 4. And that's less than 0. So the second derivative is less than 0, so it's concave down. And in part D, if g prime is the inverse function, find the derivative, write the equation of the tangent line at x equals 2. So first of all, we would want to find the point g inverse of 2. And of course, g inverse of 2 means we want to start with a y value of 2 and find what x value it came from. So g is 2 when x is 1. So that implies we're using the point 2 comma 1. And then the derivative of this is that the inverse formula we learned, g prime of g inverse. And we're finding the slope there at 2, so I'm going to go ahead and plug in 2. So again, g inverse of 2 was 1. And from the chart, g prime of 1 is 5. So my slope is 1/5, my point is 2 comma 1. There we go. So let's look at the third problem. So in this problem, we're going to start by finding h prime of 2. And here's the thing. We're not given anything about h, but we are given the line that is tangent to graph of h, which is this. So if a line is tangent to a graph, the slope of that line is the derivative. So really, there's no calculation here. It's just h prime of 2 is the slope of that line. It's 2/3. Part B. Let a be this function that's given there, and write an expression for a prime. So here's a. We're going to have to start with a product rule. So this is derivative of the first times the second plus the first times the derivative of the second. So there's your expression for a prime of x, and then find a prime of 2. So that's 36, and then h of 2, we're told, up here is 4. And then this is 3 times 8, which is 24. And h prime of 2, we found in the first part, which is 2/3. So let's see, that's 144 times 16? No, sorry, not times, plus 16, which is 160. Part C. All right, this one was a tricky one. So you're told that the limit can be evaluated using L'Hopital's rule. So basically what that means, there's two things. When I do the limit as h approaches 2 of x squared minus 4 over 1 minus f of x cubed, I can see by looking at the top, when I do substitution to start, I'm going to get a 0 on top. So if this L'Hopital's rule is involved, that means I'm also going to get 0 on the bottom, which means when I plug 2 into the bottom, I should get 0. So I can solve that for f of 2. Now, when we do L'Hopital's rule, we take the derivative of top and bottom, right? So this would be 2x on top, and down here on the bottom, it'd be negative 3 f of x squared times f prime of x by the chain rule. And it's known that it's twice differentiable. So that's this part right here. So since it's twice differentiable, that means the derivative exists, so it's continuous. Now, if it's continuous, when I plug in 2, I should get the same thing I got at the point, which is h of 2. Or sorry, yeah, that is h of 2, yeah. So that means this whole thing equals 4. Now we already found f of 2 in the first part, it's 1. So really this says that 4 over negative 3 f prime of 2 equals 4. So if I were to go and solve that, and you can do this on your own, you get negative 1/3. And then part D. Part D was just a little tricky because of the requirements of proving it. So if you know something is continuous, you have to satisfy two conditions. If we want to prove that k is continuous at 2, we have to prove that the limit as k approaches 2, x. Limit as x approaches 2 of k of x equals k prime of k of 2. So you have to address both of those things. Now, obviously this is a squeeze theorem question. If I were to take the limit as x approaches 2 of g of x, we're told that it's twice differentiable, and we're told that it's therefore continuous, and it equals 4. So I know that it's twice differentiable, it's continuous, so I know that this is true for g. We're told the same thing about h. So since that's true for both things, by the squeeze theorem, the limit as x approaches 2 of k of x, oops, my pen just stopped working, equals 4, and k of 2 also equals 4. So k is continuous. There we go.